Okay, so that's probably the simplest solution to the simple harmonic oscillator equation. Of course, there are other solutions which correspond to different initial conditions. So, for example, let's just write the equation out again. Another solution that you come across is where the cosine term is neglected and you have a sine wave with a non-zero coefficient. So let's plot the sine wave as a function of time. We'll just do one period of the sine wave. What it looks like is that. So this means that at time t equals 0, the displacement of the oscillator is 0, but the velocity of the oscillator is non-zero. So this corresponds to the oscillator getting an initial kick which moves it instantaneously to a velocity which is not 0. Let's call that velocity v at t equals 0, and we'll call it v0. Now that doesn't mean that b equals v0, right? And to prove that, let's figure out what the velocity is. So the velocity is b times omega naught minus omega naught b, sorry, plus omega naught b cos omega naught t, right? And so if you're going to have t equals 0, the cos of 0 is 1, so this term, the cosine becomes 1, and you have v at t equals 0, which equals v0, is equal to omega naught b, so that b equals v naught upon omega naught. So actually the solution for the oscillator giving an initial velocity v naught by being kicked but having no initial displacement is y equals v naught over omega naught sine of omega naught t. Of course we said sine of omega naught t was, we said that cos, well, we took out the cosine when we were inserting the boundary condition, but that's because the boundary condition, or the initial condition, is valid only at t equals 0. At subsequent times you have to put the time dependence back in, and so that's where you end up with this y of t proportional to the sine wave. So the amplitude of this sine wave here is v naught upon omega naught. Now the velocity of the oscillator, the velocity, v of t, that's equal to omega naught b cos omega naught t. So omega naught b is actually v naught, so that's cos of omega naught t. So if we were to plot the velocity as a function of time, we would get this curve, where the initial velocity is v naught. Okay? And so if the initial position is 0, it's got a velocity kick, then the position as a function of time takes the form of a sine wave, the velocity as a function of time takes the form of a cosine wave. And so that's kind of interesting. Both the position and the velocity of the oscillator, both of them exhibit harmonic oscillations. The position oscillates, but the velocity oscillates as well. And that's kind of neat. And there's a phase shift between the position and the velocity of the oscillation. And that gives rise to a way of representing oscillators called a phase space representation. So if you plot the position against the velocity, right? So here's the velocity as a function of time, and here's the position as a function of time. The initial position is 0, but the velocity initially is v0. So at time t equals 0, the position of the oscillator in this plane of velocity against time is there. And then, as time evolves, the position of the oscillator goes up and then goes back down to 0. When the position of the oscillator is maximal, the velocity is 0. So we have at t equals a quarter of a period, that's here, right? The position of the oscillator, the position of the oscillator is v naught over omega naught, and the velocity is 0, so it's there, and then it keeps going round So at half a period, it's back to zero velocity. So it's back to zero position, but it's got a maximal negative velocity. And then at 3/4 of a period, it's back to zero velocity, and now it has a negative position. So in fact, if you join all these points together and all the ones in between, you end up with an ellipse in the plane of position versus velocity, and that every period the oscillator travels once around the ellipse. And so that kind of is a common theme in harmonic oscillations, the idea that both the position and the velocity are oscillating, and if you plot one against the other, you get motion in what's called a phase space, where you have position plotted on one axis and velocity plotted on the other. That's another way of representing a harmonic oscillator.